Hello, this is Cameron Sabat, and this is Cutting to the Case with Dr. William E. Moerner, an American physical chemist and professor at Stanford University who shared the 2014 Nobel Prize in Chemistry with Eric Betzig and Stefan Hell for developing super-resolved fluorescent microscopy, a breakthrough that shattered the classical diffraction limit of light. Earlier in his career, while at IBM Research, Moerner became the first scientist to optically detect and study a single molecule, a landmark achievement that transformed spectroscopy, microscopy, biophysics, and nanoscience. His work now enables scientists to visualize individual proteins and molecular processes inside living cells with unprecedented resolution, fundamentally changing modern cell biology. He earned his bachelor's degree from Washington University in St. Louis and PhD from Cornell University before appointments at IBM Research, UC San Diego, and ultimately Stanford, where he served as chair of the Department of Chemistry. Thank you very much for joining today, and it's an honor to speak with you.
Thanks so much, Camera. I'm very excited to chat with you, and I appreciate very much your interest in this work.
Yes, yes. And I think a lot of our audiences as well, too. So I think we can start with the moment everything changed. In 1989, when you first detected that single molecule optically, did you immediately realize that this would change microscopy forever, or did it simply feel like another successful experiment to you?
Well, it's a great question, and it's you have to really turn your mind back to the 1980s and realize that there was a lot of interest back then
Mhm.
in storing data in new ways using light. And I was working on that problem, how to store data with light at low temperatures by making marks in solids and the wavelength of the light that's used or the color of light that's used. And it was understanding that concept or looking at fundamentals undermining that concept that led us to believe that we could detect a single molecule. You see, the problem at that time is that people thought you could not detect a single molecule, and so they were very skeptical at the beginning. And so, since I felt that it was possible, we pushed forward. My postdoc, Lothar Kator, and I pushed forward to get to that single molecule limit and to prove it multiple ways and so forth to be very sure that we had it before we published. And at that time, yes, it did feel like a major step. Uh, of course, what you cannot envision, okay, when something very new has been observed in a relatively esoteric low temperature experiment, how far it would go, how far it would expand and explode and so forth and produce new applications. But that's the way fundamental research works.
Mhm.
Research that's at the boundaries of what has been done has the possibility to discover new things and open new doors.
Yes, yes. And what a wonderful kind of explanation of the experience of undergoing such a huge scientific discovery. Many of these Nobel winning discoveries seem obvious only in retrospect. I'm curious, what's the biggest assumption your field held that turned out to be completely wrong?
Well, one of the things that we thought at that time was that if you cool samples to very low temperatures, a few degrees Kelvin, you of course freeze everything and you stop many, many, many processes. And we thought that molecules that were stable at low temperatures would just have a fixed single wavelength. Think of it like a spike in the frequency spectrum, just sort of sitting there and not moving anywhere. And so one of our biggest surprises right at the beginning was to start observing things that we hadn't seen before. We all of a sudden started seeing that the molecules might be at one frequency. So this is like a wavelength axis horizontally, and this is like the signal from the molecule. We saw that they would jump from one wavelength to another, or one color to another, even at these low temperatures, which was fascinating and surprising to see. My postdoc at the time, Pat Ambrose, just came running across the hall. My office is right across the hall from the lab. And says, "The molecules are jumping around. The molecules are jumping around." And it was one of those very exciting moments of seeing things that weren't seen before. Again, at that time, we didn't know what the utility of this would be, but it was a fascinating physical effect that we could explore and try to understand.
Absolutely. And About this idea of finding these molecules, you've made one of history's most important academic discoveries inside an industrial research lab. Do you think today's research ecosystem still gives scientists the freedom to pursue similarly risky ideas?
Well, unfortunately, I think it's a little bit scarce these days to find that. There may be some places where you can do it, but in those days, it was the great glory days of IBM Research Laboratories, Bell Laboratories, General Motors Laboratories, and a few others where money was dedicated to doing fundamental science,
Mm.
where you could publish the results and build up a reputation on the outside world and basically explore matter and ask questions about things that hadn't been done before. So it was wonderful to have that happen. There's not as much of that in the corporate environment now, although there are some biological research centers where there's a lot of intellectual freedom now. But it turns out that that was very special for the time, and that kind of work now really appears mostly in the university environment.
Yes, yes. And I'm curious because a lot of Nobel laureates in science specifically talk about failure. Um, are there any experiments that failed in your career that ended up teaching you the most or became stepping stones to future discoveries?
Absolutely. In fact, I believe that if you're not working at the edge of a field, ready to explore and discover something new, you won't be finding basically failures. And so, having a certain number of failures is a good thing because each of them can be a learning experience. So,
Mhm.
this is a message to all scientists who want to work in this kind of arena. Failures represent an opportunity to ask why it happened and what is it about the system that you did not understand. Because if you turn that failure into a learning experience, it feels so much better. So the failure I can mention in this respect is that before we detected single molecules, we were studying, as I said, that optical storage business, and signal to noise is very, very important. We were making bits out of millions of molecules, but still, the location of frequency away from molecules is represents a background, represents a difficulty for detecting very small marks. And so you want to understand what sort of noise sources are present. So we were looking at this signal away from the molecules, and we felt that there should be a kind of noise, a spectral noise, which we called statistical fine structure, which was something that is coming from the different numbers of molecules present at each wavelength. And so I was trying hard to detect that. And we made very nice samples out of polymers, molecules in polymers, and we're studying them. And we were looking for this spectral feature. But each time we might observe it, we would say, it's almost there. And then we measure it one more time, it's different. So it's slightly different the next time. And so you are frustrated. Obviously, with any physical effect, you have to observe it multiple times and confirm that it's really there. And this was really frustrating. So it was many months spent on that. And finally, out of all total frustration, one weekend, I just said, nope, we're going to stop this polymer. We're going to go to a crystal. We're going to take a very, very stable molecule, and I could make a sample, a crummy sample, actually, just on a hot plate over the weekend, and put it in the spectrometer, and immediately these noisy features appeared. Although remember, they're not time-dependent noise; they're static, and so you should see the same structure if you measure it again and again.
Mhm.
If you move to a new piece of sample, you see a different structure. So this was a signature directly of the number of molecules that were present in a statistical sense. So sorry, it's a little bit esoteric, but the size of this signal scaled as the square root of the number of molecules, not linearly with the number of molecules. Usually, when you make a sample, you put in 10 times more molecules, you get 10 times more signal. But with this signal, you get the square root of 10 more signal. So it was really deep and interesting and fascinating. And it led to the single molecule business because once we saw that, we said, hey, maybe we can detect singles.
Yes. Yes, and with those single molecule mindsets, I mean, once that came out and you learned how to study one molecule instead of billions at once, how did that fundamentally change the kinds of scientific questions you've asked? I can only imagine that's incredible.
Yeah, that's a great question. So the excitement is that now you can explore whether all the molecules that you assume to be the same are really the same. In fact, they aren't. There's heterogeneity. That is, the different molecules may have different behaviors, different line widths, or different other properties. So scientists all over the world jumped on this and started measuring and used every method that they could think of, applying electric fields and magnetic fields and looking at the orientation of molecules by polarization effects and so on, and publishing and publishing, building the field, and because we wanted to understand all of the properties as well as the heterogeneity that's there. And this heterogeneity thing, I'm sorry to make it seem mysterious, but in conventional experiments that are not single molecule, you average over many millions or billions of molecules when you measure, let's say, a spectrum. And when you can do it one by one, you can see if they're all the same or not. And that's the explosion of interest that, of course, extends into the biological arena now.
Could you speak more about this extension into, I know as a medical student, you saw this coming a mile away. Very curious.
Well, it is a fascinating thing for physical scientists to make the jump into biological experiments, and it's challenging. It was a challenging idea for me. I had to learn more and more when we did that. But the crucial experiments involved showing that you could do this at room temperature. So a bunch of scientists in the mid 90s showed you could also do it at room temperature, and we agreed. And so many of us moved to room temperature, and moving to room temperature was the opening the door to looking at biological systems on the big scale. Of course, you can study certain antenna proteins and various other things that are involved. You can measure their optical properties at low temperature, but room temperature gives you access to so much more. And so the motion and move to room temperature is one of the reasons I left IBM, so I could start exploring biological systems that were not really being studied at the laboratory at that time, and broaden the field. So that's a major step, and it is another reason that the field exploded even more. Looking inside biological systems, you can zero in on, let's say, a specific protein that's been labeled, and there are many copies in the cell, but if you measure them one by one, you can see how different they are. And it's quite reasonable to believe they can be different, either by nucleotide state, if they're enzymes, or a local environment, if they're moving around, their ability to move changes depending on where they are, and so on and so on. So there's a tremendous amount of this heterogeneity I was describing.
Yes, and about kind of the back back to the experience of also going through this whole process. If a grad student came to you with an idea that every advisor thought might have been unrealistic, how would you decide whether to encourage them or talk them out of it?
Well, I would do that by analyzing the idea in some detail. We would have to think about it, and is it reasonable to believe that it can be observed? So that sort of a question is quite important, because you can always come up perhaps with something that's impossible or nearly impossible to do, and you don't really want to spend your life tilting at windmills. So it's actually one of the interesting things about our field, that we want to find areas to explore that are new and different, but are not so difficult that you never get any results. Imagine that poor graduate student working away, and getting nothing for year after year after year. That's really a downer.
Yeah,
So it's important to have some things that work along the way. And
yeah,
we make that decision based on analysis of the signal to noise. How strong is the signal? How well can you make the sample? What kind of wavelengths do you need to explore this? what property do you want to explore or determine, and that's those sorts of things.
Mhm. Absolutely. And you were in Brazil when Stockholm called. After the excitement wore off, what was the first thought that crossed your mind?
Well, it was quite a fascinating experience, as you say. I
Sure.
was in Brazil, and I was too cheap to pay for having my cell phone work in Brazil, and so I did not get the call. But what I did get is a WhatsApp because we
You
had
got it through
Wi-Fi.
WhatsApp.
Yeah, and so my wife sends me the note, turn on your phone. And I'm like, uh-oh, what's going on here? And realized that it was probably the Nobel people calling. So they were able to call her. Actually, I beg pardon. The Associated Press called my wife
Mm.
because you see the Nobel Committee, they try for a while to reach the laureates. And if you can't reach them, then they have to give up after 20 minutes or something and go live because the press is waiting for the press conference. So the AP called my wife. So, of course, the very first feelings were, oh my God, my
Yeah.
life is going to change right now. And you are never ready for that, and you have to roll with it, and so on. So it was quite an exciting time.
Yes. Yes. Thank you for walking us through that experience. Something very, very few people will ever really be able to experience. And thinking about this, how much of your career has been careful planning versus recognizing unexpected opportunities when they appeared? I've heard a lot about the kind of nexus of skill and luck and all of these things coming together, especially in science. It's so trial and error focused. Um, could you maybe speak to that?
Well, most of my career has been directed toward exploring new things. That is, if something has been measured multiple times before, or the technique has been used many, many times, then I'm interested more in new techniques that might open new arenas.
Hmm.
So that is been a driver for a very long time. Now, your ability to invent a new technique or to discover a new observation is, of course, limited by the community, what's known at the time. I've had spectacular collaborators, graduate students, postdocs, and so on, all along who have helped tremendously to, increase if you like, the creativity of our local interactions, and that's been fruitful. And so I have not really said we're going to plan out one problem for the next 20 years, except to say we're going to explore single molecules for as long as we can, always looking for new properties that have not been observed before. And that's worked to uncover quite a lot of interesting things through this whole story about single molecules and moving to super resolution and studying cellular systems in detail.
Yes, and really positioning yourself in a good kind of angle to maximally cut through and and discover. Um,
hmm hmm I
yes,
should say one thing about that. Let me just mention that
please.
I've made um, great progress through very fruitful collaborations. In other words, to move into more biological areas, it really didn't make sense to start from ground zero. Okay, but to rather collaborate with an expert because we could bring our skills together and get going faster. So in those early days, there was work with Larry Goldstein and people that were studying kinesin motor proteins. So we could learn a lot by combining efforts. And that has been very successful again and again throughout, collaborations with Lucy Shapiro on lots of interesting bacterial systems, collaborations with Stanley Chi and others in more modern times. So there's uh, a tremendous fruitful aspect of that kind of environment.
And thank you for speaking to the power of collaboration as well in modern science, especially. It's vital. I mean, it's yes. And I'm also curious to see, artificial intelligence is also transforming image analysis. We're talking about collaborations between humans. I mean, collaboration with technology as well. What aspects of microscopy do you think AI will genuinely revolutionize, and where do you think it might be overhyped?
Well, it's a big question for this modern time. Lots of discussions about AI, but you center already on the most important overlap area, which is on images. A lot of AI systems, especially convolutional neural networks, are designed for analyzing arrays. And so images are arrays of data, and we've been using it for some time to help analyze the thousands to millions of images that we record of single molecules. The other thing that can be done with the AI sort of approaches is to invent new ways of imaging, new ways of observing the molecules, because a single molecule produces a spot on a camera. And if you change the shape of that spot by designing special optical components, you can actually get more information about what the molecule is doing, its orientation, its color, and so on, its Z position, that is axial position. You can directly record that from a 2D camera, two-dimensional camera, by this approach. And so we've utilized that quite a lot in our more recent work. You can even ask the AI to help you refine millions of possible new shapes for the way the molecule appears. And that's a problem that has an error function and so forth that would be directly useful in an AI-like calculation. Now, the other aspect of all of that is whether AI can design your experiments for you and pick out which molecules you want to use and so on. I mean, that's something that can be helped by AI, which can sort through millions of papers now or thousands of articles and so forth with the reporting properties. That's always been a challenge for modern science. There's so much that's been published, so much that's out there, and it's really very, very hard for one individual to plow through all of that in a deep way. And so that's one way that it helps to be as sort of an assistant. But it's a much more difficult problem to be creative on a deep level to change and in fact invent something completely new, which has not been in the previous literature. So it couldn't be basically, learned by the learning process.
Mhm. And obviously there's that ever-growing concern of people offloading their um, cognitive capacity onto AI and just essentially becoming dumber as they
Hmm.
let it think for them. And I
Hmm.
think that can only be pervasive at this point in
Yes.
science. I'm sure you're very concerned about that. Uh,
Yes.
what might you say are some strategies to help mitigate that, especially among the younger generation that's still in training?
The most important strategy is that you have to check every result. You simply have to go in and look closely to see, does that make sense? Use the scientific skills that we all learned early on to explore something that's new that's been stated and ask for the things that would prove that it's really true.
Mhm.
I don't know how if you've seen this, but I have with AIs. When I hear something that's completely wrong, I immediately say that's completely wrong. And the AI says, "Oh yes, you're absolutely right. It's blah blah blah," and so on. It's sort of like, "Oh, it knew it already, and now it's going to agree immediately." And I don't understand that sometimes, but anyway, it sort of illustrates the problem. It states things with great certainty, but they may not necessarily be correct. So you have to always be validating and checking results. We do that with any of these things that we calculate that I described earlier. Uh, uh, Basically, compute many, many examples and get an error. How accurate is the final result? How correctly can you predict some number, let's say? And those kinds of statistical tests are, I think, essential.
Yes, crucial, crucial. And if we could interview you again in 20 years, what breakthrough in molecular imaging would you hope had become routine? This can also be alongside that AI comment or some other thing that you're looking toward.
Well, it's always difficult to predict the future. And so I cannot really do much on that point simply because what has happened in the past many, many times, and I have many examples, is something we didn't predict. You have to be exploring near the boundaries and have an open mind to surprises. And that open mind to surprises is crucial to, open new doors. So there will be many, many new things that happen, more advanced microscopy methods, more advanced biological tools that one can use to control the biological systems. And you see many of them now through CRISPR and other examples of modifying systems very carefully. And there's a tremendous world out there that we can keep working on just because we're working on complex systems that are complex enough where there's many, many new things to be discovered. If everything were very well defined, let's say a perfect crystal, how many new things are you going to find in a perfect crystal? The number may be smaller than if we're in this wonderful set of biological environments that are so complicated and exciting. Now, I want to say briefly, since we didn't really mention it, one big surprise that was super important for super resolution was observing that molecules blink on and off, that they turn on and off, and there's some ways to optically control this at room temperature. So we did not expect that either. We saw some interesting things at low temperature was when molecules were jumping around, but at room temperature, the absorption lines and fluorescence are much, much broader. Nevertheless, they can still turn on and off because there's local changes in the chemical environment of the molecule and other sorts of physical processes that give us another tool, which is one of the keys to achieving super resolution.
Yes, yes. And this this work of super resolution and biology, it sits at the intersection of so many different disciplines, really. I mean, with chemistry and engineering and physics. Do you think the most exciting discoveries now happen between disciplines than rather than within them? Because I've also noticed as an outsider to the scientific discipline, at least, that there is a lot more interdisciplinary work being pursued. And how might that affect the structure of academics moving forward? I know you were chair of chemistry at Stanford University. Might there be more, I guess, how would departments change? How does that work?
Well, it's an interesting challenge. It's a great question. It is true. I believe that many new discoveries are at the boundaries between disciplines, which is why we embrace these interdisciplinary projects. And it came also from those earlier days of mine at IBM, because that was also present in that environment of the corporate research lab. Many people come there with their own skills, whether they're an organic chemist or whether there's an optics expert or whether they're a magnetics expert. But when there's a problem, all people with different backgrounds are working together. And that's very different from the sort of long ago university model of pillars of excellence around one professor. And so we're breaking down those pillars, and that's happened a great deal now. And there are students who can join different groups, even if they're admitted into one department. And so, for example, I'm a physical chemist here, but we're doing biology. But I used skills from electrical engineering, that was one of my early studies in undergraduate school, to achieve and be able to understand and appreciate these precision measurements that we do. It's really fundamental precision measurements, of course, that underlie all of this. If you want to observe individual molecules and observe how you can control them to achieve super resolution. You're muted.
Apologies. Thank you. Um, and people often imagine Nobel laureates as exceptionally confident. Was there ever a period where you genuinely questioned whether your research direction was worth pursuing, and what got you through?
Yeah, another good question. So each time that I decided to learn about a new field, which I had to do, moving into studies of biological systems, there was always a period there where I felt like, wow, there's way too much that I have to learn in order to be able to contribute at this level. So I learned early on that it's okay to continue to feel like you're a student. It's okay to ask questions. It's okay to admit you don't know everything. And it's really coming from, yes, some sort of internal uh, confidence that I'll make it through that. But that is, I'm happy that we could do that with our collaborators, et cetera, because they were really our teachers. Um, so that's one of the ways to think about this. I also was searching for people who would appreciate this, would appreciate that bringing our physical skills to some of their biological problems would be a step forward for them. And they also had that openness instead of thinking that I've already understood all this and you'll never understand it, Moerner. So they welcomed our interactions.
Absolutely. Um, and two final questions as well. After spending a lifetime answering questions about molecules, what scientific question are you personally still dying to know the answer to? Like if Richard Feynman came in and asked you.
Well, one of them could relate to this interesting challenge. When you pump a molecule with light, you bring in an electromagnetic wave, and the molecule interacts with light through its dipole, which is one of its quantum mechanical properties. Now, when you excite a molecule, you know there's a ground state and an excited state. The molecule, once it's in the excited state, can sit there for a while before it emits light, if it's going to emit light. And so, what is going on? What is going on during that time? It's sitting there, it's excited, but it hasn't emitted light. And then at one instant, all of a sudden, light appears. And by that, I mean another wave of the oscillation of the dipole emits light going to long distances. So that's still very puzzling, how there's this discontinuous change that occurs all the time in these molecules. And it's fascinating to think that that can be underlying these new images that we can create. Um, I can show you one if you would like, that might illuminate some of this part of the story. So um, okay, so let's do this here. So here is an image of a cell, which I believe you can see just fine, right? And
Sorry,
so
I'm on mute. Yes, I can.
okay, good. So this is a eukaryotic cell. The nucleus is the dark region in the middle. And so in this perinuclear region, there are some fascinating structures here. And these structures have come from our super resolution microscopy to define the locations of the viral genomic RNA of the SARS-CoV-2 virus. This
Wow.
is a cell infected with SARS-CoV-2.
Hmm.
Work by my group here with the first author, Leonid Andronov. This is, to me, it's a spectacularly interesting structure. All of these certain sort of little cluster objects turn out to be replication factories where the virus has taken over the cell, and the virus has provided its own enzyme for copying its own viral genomic RNA. So each one of them has hundreds to thousands of the viral genomic RNA stored in it. This is basically packaged in a little membrane, And so there's several other key proteins that are all inside there. And so this is so unbelievably interesting to me because, millions of people died from this disease, COVID-19. And this is only one cell and how it has been attacked by the viral genomic RNA and the enzymes and proteins that it produces. So we ended up studying 29 different proteins, the whole proteome of the virus in recent work just published. So bottom line,
Wow.
how is this really happening? Every detail or every step along the way, you would like to understand. This is a snapshot of a fixed cell showing the structure that had been created at a certain time. You can do it at different times. You can also do other sorts of time-dependent experiments. We, of course, need better methods that can work at higher speed because it takes a little time to get this super resolution image from the data in this case.
That's incredible. Thank you so much for sharing. I mean, this is really fascinating to see, and you've essentially done the whole proteome, which is just insane to imagine. Do you think that there might be in the future videos instead of just single images and snapshots in time?
Well, there are already videos on a certain time scale. In other words, if you have things that only move slowly or change slowly, then you can measure this again and again and again. This image here took many millions of images to build it up. And so this particular one took many minutes to record. But if you examine smaller areas and run the camera faster and have faster blinkers and various things, some people have already worked at video frame rates for small fields. Video frame rates, that's 30 hertz, which is a huge step. Uh, if we stop trying to get all of the super resolution information and just want to watch, it's already been possible since the beginning of single molecules to observe their motion when they're isolated, when they're not piled up on top of one another. When they're piled up a lot, then you have to use these blinking methods or other methods to achieve super resolution. But when they're by themselves, you can localize their position far below the diffraction limit and watch them moving around and measure what kind of diffusion process you have, and is it being affected by binding to other structures and so on. So right now this tracking of singles is a great field of study and complementary, I would say, to this kind of super resolution image. Sorry, you're muted again. You're muted.
Sorry, this is the IBM with the boy with the bouncing ball and the Brownian motion and all of that single molecule stuff as well. That's very exciting though that they're starting to do blinks and frame rates as long as you don't do super resolution. So I want to be respectful of your time. I did promise 30 minutes. I don't want to take up too much of your time. I just wanted maybe one thing that you can leave our audience with. If there's any advice that you'd like to give, just as a reminder, our audience is primarily composed of medical students, young scientists, trainees, so anyone in early career, really.
Mm-hmm. Yeah. Well, that's fantastic to have the opportunity to talk to this community. And it is an incredibly important work that you're all doing. I want you to keep moving forward, keep learning, keep pushing, and keep asking the deep questions. How does this really work? How do we continue to produce new results? How do we keep an environment where we can produce new results? Because we have a number of attacks on science going on these days, which are very serious, and I'm very concerned about them. But you're already at the forefront creating new things, and so keep it up and don't let failures stop you. As I said earlier, those are learning experiences. You keep moving forward.
Yes. Thank you. Thank you very much. And ending on a note of perseverance is very um, refreshing to hear, especially in this current climate of science. So Thank you very much.
My
So
pleasure. Yeah.
yes, that's the end of our interview. This has been Cutting to the Case, and thank you again. And this is Cameron signing off.
Thank you.